Welcome to NPTEL MOOCs course on Computer Vision and Image Processing Fundamentals and Application. In my last class, I discussed the concept of image transformation. The transformation converts the spatial domain information into frequency domain information. Mainly, it is the mapping from spatial domain into frequency domain. The transformation does not change the information content present in a signal, and transformation is quite useful for compact representation of data. And also I discussed the concept of orthogonal transformation. So in the orthogonal transformation, I define the transformation matrix, that is T inverse is equal to T transpose. Then in this case, it is called the orthogonal matrix, and the transformation will be orthogonal transformation. And if I consider the transformation matrix is a complex matrix, then T inverse is equal to T complex conjugate transpose, that is called unitary matrix, and the corresponding transformation is called the unitary transformation. And I also highlighted that DFT, the discrete Fourier transform, that is not unitary. So I can make DFT unitary by defining the DFT, so that I am getting the unitary DFT transformation. After this, I discussed the properties of unitary transformation. So three main properties I want to highlight again. One is energy preserving property. So in the energy preserving property, if I do the transformation from the spatial domain into frequency domain, so I will be getting transform coefficients. So most of the energy is available in few transform coefficients, that is called the energy compaction property. And one is the energy preserving property, that is mainly the energy in the data domain is equal to energy in the frequency domain. So that is called the energy preserving property. Energy in the data domain is equal to energy in the transform domain. Also I discussed another important property, that is the decorrelating property. So my original data is highly correlated, and after the transformation, the transform data will be less correlated. So for this I define the covariance matrix. So based on the property of the covariance matrix, I can define the decorrelating property. Last class I defined the DFT unitary matrix. Now today I will discuss one transformation, that is called the DCT, the discrete cosine transform. And after this I will discuss another transformation. The transformation is KL transformation. The DCT transformation is a orthogonal transformation. Orthogonal means the T inverse is equal to T transpose, that is the orthogonal matrix, and the transformation is the orthogonal transformation. So let us see what is the DCT, the discrete cosine transform. So first I am considering 1D discrete cosine transform here. So I am considering the data vector is f, I am considering. So it is f naught, f1 like this, fn minus 1, and I am considering the transpose because column vector I am considering. After this, the DCT can be defined like this. So DCT fck, the DCT of the input sequence is fn, is defined by this equation. Here you can see the fck is equal to alpha k, n is equal to 0 to n minus 1, fn cos pi k divided by twice n plus 1. So in DCT, this cos pi k divided by twice n plus 1, that is the transformation kernel. And I can also get the reconstructed data, that is the inverse transformation, the inverse DCT I can determine. This is the inverse DCT. So fck, from fck I am determining fn. Fn is the original data vector that I can determine by inverse discrete cosine transform. And in this case I can define alpha k is equal to 1 by root n corresponding to k is equal to 0, and it is equal to root 2 by n for k is equal to 1 to n minus 1. So this is the definition of 1D discrete cosine transformation. And this transformation I can write like this. So f is the DCT, that is the transform data, and TC is the transformation matrix corresponding to discrete cosine transform, and F is the original data. And in this case, the transformation matrix Tc and corresponding elements of the transformation matrix I can write like this. So, TKL, the elements of the transformation matrix. So, TKL is equal to alpha k cos pi k divided by twice n twice L plus 1. So, this is the elements of the transformation matrix. And in this case, the transformation matrix is real, because I am considering cos pi k divided by twice n. So, that means in this case I am having the real values. So, that is why the DCT is a real transform. But in case of the Fourier transform, I have the both cosine and the sine component, the real component and the imaginary component. So, that is why it is complex. But in case of the DCT, I have only the cos component, the cos pi k divided by twice n twice L plus 1. So, that is why the DCT is a real transformation, and the DCT is an orthogonal transformation. So, here you see the TC inverse is equal to TC transpose. So, that is why it is the orthogonal transformation. Now, I want to show the relationship between the DCT and the DFT. So, in my first equation you can see here, this is the definition of the DCT. FCK is equal to alpha k, Fn is the input data sequence, n is equal to from 0 to n minus 1, Fn cos pi k divided by twice n plus 1. So, this is my FCK is the DCT. Now, this equation I can write in this form, you can see, because already I have explained that in case of the DCT we have only the cos term, there is no sine term, that is there is no imaginary component. So, that is why I am considering only the real part of the exponential function, this exponential function I am considering. So, I am considering the real, that means the cos term I am considering, the neglecting the imaginary term, that is the sine term. And after this I am considering another sequence, the new sequence I am considering, that is f dash n. So, what is f dash n? F dash n is equal to Fn corresponding to n is equal to 0 to n minus 1, and otherwise it is 0. So, I am defining a new sequence, the new sequence is f dash n. After this DCT expression I can represent in this form, you can see FCK real, and in this case I am considering n is equal to 0 to twice n minus 1, because in this case you can see this 0, that means I am doing the 0 padding up to twice n minus 1. So, f dash n is equal to Fn for n is equal to 0 to n minus 1 and 0 up to twice n minus 1. So, what will be the length of my sequence? The length of the sequence is from 0 to twice n minus 1, that means it is a twice n point sequence. So, in this case for corresponding to the new sequence is f dash n. I can write this expression, the expression for the DCT. So, if you see this expression and you can see this term, if you see this term from this to this, because you know this expression, suppose if I consider the DFT is n is equal to 0 to n minus 1 Fn and e to the power minus j twice pi divided by n nk. This is the definition of n point DFT. So, if you compare this one and this one, then it is nothing but it is the twice n point DFT. That expression is nothing but it is a twice n point DFT. So, from this expression you can see the relationship between DCT and the DFT. So, how to get the DCT from the DFT? If you see this block diagram, you can see the input data sequence is F0, F1 up to Fn minus 1. This is my input data sequence. After this, I want to get a new data sequence. The new data sequence is f dash n. So, for this I have to do the 0 padding. So, I am doing the 0 padding. So, what will be the length of the new sequence? The length of the new sequence will be twice n. So, it is from 0 to twice n minus 1. And after this, I am computing the twice n point DFT. So, that means I am computing this part, twice n point DFT. After this, you can see I am doing the multiplication by alpha k and also by this e to the power minus j pi k divided by twice n. So that is why I am doing multiplication by alpha k e to the power minus j pi k divided by twice n. And after this I am considering one operation, that operation is the real. So I am considering the real part of this, and I am getting the DCT of the sequence. So you can see that you can obtain the DCT from the DFT by this process. So first I have to do the zero padding, so that the length of the sequence will be twice n, and after this I have to calculate the twice n point DFT, and after this I have to do multiplication. The multiplication is alpha k e to the power minus j pi k divided by twice n, and after this I am doing one operation, that is the real part I am considering, and I am getting the DCT. So that means the DCT can be computed by using the DFT. So in this slide I am showing the another interpretation, that is the relationship between the DCT and the DFT. In this case you can see, again I am considering one new sequence. The new sequence is generated from the original sequence. The original sequence is fn. So this is the new sequence f dash n. So what is f dash n? F dash n is equal to fn corresponding to n is equal to 0, 1 up to n minus 1, and it is f twice n minus 1 minus n corresponding to n plus 1 up to twice n minus 1. So what will be the length of the new sequence? The length of the new sequence is twice n point. After this I can determine the DFT of this sequence. I can determine the DFT of this sequence. Just you can see the mathematics. After determining the DFT of the new sequence, finally I am getting the FCK. FCK is nothing but the DCT of the sequence. So I am getting the DCT of the sequence, that is equal to e to the power minus j pi n into nk alpha k into fk. So this is I am writing here. So this is very important. This is a very important representation. So how to get the DCT from the DFT? So what is FCK? FCK is nothing but the DCT of the sequence is equal to e to the power minus j pi n nk alpha k fk. So you can see, so by using this approach also you can determine the DCT from the DFT, because the DFT already you know how to compute the DFT. So there are many algorithms like FFT also you can use to determine the DFT, and by using the DFT you can determine the DCT of a particular sequence. So for this I have to define the new sequence. The new sequence is f dash n. So this is the new sequence, and that is the twice n point sequence. So it is a twice n point sequence. So by using this method I can determine the DCT from the DFT. Now if you see this extension, the extension what I have done, the extension is something like this: f dash n. I am having the new sequence, f dash n is equal to fn corresponding to n is equal to 0, 1 up to n minus 1, and is equal to f is equal to twice n minus 1 minus n for n is equal to n plus 1 up to twice n minus 1. So I am getting the new sequence like this. The DFT is nothing but the periodic extension of data. This is nothing but the periodic extension of data. This is the case for the DFT. In case of the DCT, if you see the second case, this is nothing but the symmetric extension of data. This is nothing but the symmetric extension of data. And this is the symmetric extension of data. What I have done here, that is the symmetric extension of data. So in case of the DFT, it is nothing but the periodic extension of data, but in case of the DCT, I have the symmetric extension of data. Now in this case you can see the previous discussion, you can see the input sequence was the n point sequence, and after this I am generating a new sequence, that is the twice n point sequence, and after this I am determining the DFT. So that is a twice endpoint DFT, and from the twice endpoint DFT I am getting the endpoint DCT. So what I discussed in my last slides, that from the input sequence is the endpoint sequence. After this I am having the new sequence is twice endpoint sequence, and after this I am determining the twice endpoint DFT. So this DFT is the twice endpoint DFT, and from the twice endpoint DFT I am calculating the endpoint DCT. So you can see, in case of the DFT, the endpoint data is represented by the twice endpoint DFT, but this endpoint data is represented by endpoint DCT. So you can compare the energy compaction property. In the first case, in the DFT case, the endpoint data is represented by the twice endpoint DFT. That is, if I consider the new sequence, suppose that is the twice endpoint data is represented by twice endpoint DFT. And in case of the DCT, this twice endpoint data is represented by only endpoint DCT. So you can compare the energy compaction property, that is, the energy compaction of DCT is better than DFT, because the twice endpoint data is represented by twice endpoint DFT, but in case of the DCT, the twice endpoint data is represented by endpoint DCT. So that is why I can say that DCT is better than DFT for the case is the energy compaction property. And in case of the DCT, I have already explained this one. This is nothing but the symmetric extension of data around the point is n-1. This is the case of in the case of the DCT, I am doing the symmetric extension of data around the point n-1. In this case, again I have shown the concept of the DFT and the DCT. DFT is nothing but the periodic extension of data, and DCT you can see it is a symmetric extension of data around the point n-1. So you can see here, because of, in case of the DFT, because of the discontinuity, you can see the discontinuity here, discontinuity, this is the discontinuity. So there is a jump in the discontinuity, and in this case we have the high frequency distortion, and this high frequency distortion, it is called the Gibbs phenomenon. Gibbs phenomena. This is the high frequency distortion because there is a jump in the extension. The extension is around the point n-1. In case of the DCT, you can see the transition is very smooth around the point n-1. So transition is very smooth around the point n-1. So that means the high frequency distortion will be less in case of the DCT. So I have explained in the slide here that one is the high frequency distortion, and in case of the DCT, high frequency distortion is less because we have smooth transition at the boundaries, around the point n-1. But in case of the DFT, because of this abrupt change of this value, you can see that we have the high frequency distortion, and this is called the Gibbs phenomena. And in this case, you can see the energy compaction property of the DFT and the DCT. In this example, I have shown the input image is this, and I am considering the DFT first. You can see the energy compaction here I am showing in the graph, and in case of the DCT, you can see this energy compaction. Energy compaction means most of the energy is available in few coefficients. In DCT, it is better than the DFT. And in this second example, in this case, I have shown the image reconstruction after performing the discrete cosine transform. So in this case, I am considering one image, input image, and I am determining the DCT of this image. So I have the transform coefficients. You can see the DCT coefficients here, all the DCT coefficients. These are the DCT coefficients, and I have already explained that the most of the energy is available only in few coefficients. So that is why I am considering only the high value coefficients. only this part I am considering, neglecting all the remaining coefficients. Only this portion I am considering, and after considering these coefficients, I am reconstructing the image. So this is the reconstructed image, and you can see if I compare the visually this image and this image, visually you cannot see the significant difference between the input image and the reconstructed image. So you can see that here that DCT and DFT I have explained. So from the DFT you can determine the DCT. I have shown two approaches, and first you have to define a new sequence. From the new sequence I have to calculate the DFT, and from the DFT I can determine the DCT. DFT you can calculate by the popular algorithms like FFT, the fast Fourier transform, and from this you can easily determine the DCT. And if I want to compare the DCT and the DFT, you can see DCT has more advantages as compared to DFT. The first advantage is the DCT is a real transformation, DFT is not a real transformation. The second point is the energy compaction property. So if I compare the DFT and the DCT, so DCT is better than DFT. And after this I have shown that the one example how to reconstruct the image from the DCT coefficients. So only we have to consider few coefficients based on the energy value, and we can neglect the remaining coefficients because most of the energy is available only in few coefficients. So you can see the difference between the DCT and the DFT. Now I am showing the 2D DCT, the two dimensional discrete cosine transform. So this is the extension of only 1D DCT, you can see here. So FC K1 K2, so K1 is the index corresponding to the one direction, that is the x direction suppose, and K2 is the index corresponding to the y direction. And I have alpha K1, alpha K2, and my input 2D sequence is this f n1 n2, and my cost term, the two cost terms, cos pi K1 divided by twice n plus 1, and cos pi K2 divided by twice n 2 plus 1. And from this expression I can determine the inverse DCT. So I can determine the inverse DCT by using this equation. Now already I have explained the two properties, one is the separable property of the kernel and also the symmetric property. So because of the separable property, I can implement the transformation, the 2D transformation, first along the row direction in one direction, and after this I can perform the 1D transformation in another direction. So that means for the 2D DCT that can be implemented by one dimensional DCT. So first I can perform the 1D DCT along the columns, and after this I can perform the 1D DCT along the rows. So this is because of the separable property of the kernel. Here I have shown the procedure. So my input data sequence is f n1 n2, and first I have to apply the DCT, one dimensional DCT along the rows. So in this case I am getting this one f k1 n2. So DCT is applied along the rows, and after this I am applying the DCT along the columns. So after this I am getting the 2D DCT, that is the two dimensional discrete cosine transform. So this is about the DCT. The next I want to discuss the concept of dimensionality reduction of data. So up till now I discussed that these two transformation, one is the DFT, another one is the DCT. In case of the DFT and in case of the DCT, the transformation kernel is fixed. Already you know what is the transformation kernel for the DFT and also for the DCT. Now I am going to discuss another transformation, that is called the KL transformation. In the KL transformation, the transformation kernel is not fixed. The transformation kernel depends on the statistics of the input data. That is the difference between the KL transformation and the DCT and the DFT, or maybe I can consider the discrete sine transform. I have not discussed the discrete sine transform. So for all these transformation, DCT, DST and also the DFT, the transformation kernel is fixed. In the KL transformation, the transformation kernel depends on the statistics of the input data. Now let us discuss about the KL transformation. So that is the Kerr-Hunen-Love transformation. That is the KL transformation. So what is the principle here? So first I am considering a population vector. Suppose a vector is considered, that is the x is a vector. The population vector is considered x1, x2, xn. And for this vector I can determine the mean. The mean I can determine, that is the mu x I can determine. So this input vector is the n dimensional vector. So it is n dimensional vector, you know, this is n dimensional. N dimensional vector. Corresponding to this n dimensional vector, I can determine the mean, that is mu x I can determine, and also I can determine the covariance matrix. The covariance matrix is Cx. That is, what is the dimension of the covariance matrix? It is n cross n. So I have the mean and the covariance. Now if I consider the elements of the covariance matrix, suppose Cii, that corresponds to the variance between xi and the xi. Another one is Cij, that is the covariance between xi and xj. And one important point is the covariance matrix, that is Cx, is a real matrix, and also the symmetric matrix. So it is a symmetric matrix. Then in this case it is possible to find a set of n orthonormal eigenvectors. So it is easy to find the n number of orthonormal eigenvectors. So in this case I am considering Ei is the eigenvectors. And corresponding to this eigenvector, my eigenvalue is lambda I. This is my eigenvalue. So from the covariance matrix I can determine the eigenvector, and after this the corresponding eigenvalue I can determine. These eigenvalues I can arrange in the descending order of the magnitude. You can see here the eigenvalues are arranged in the descending order of the magnitude. So lambda I is greater than equal to lambda I plus 1, corresponding to I is equal to 0 to n minus 1. Now the next step is I want to determine the transformation matrix. The transformation matrix is A. So this is my transformation matrix. The first row of the transformation matrix is the eigenvector corresponding to the largest eigenvalue. So in this case I am considering E1, suppose. So this is the first row of the transformation matrix is the eigenvector corresponding to the largest eigenvalue. And like this I am considering what will be the last row of the transformation matrix is the ENTN, that is the last row of the transformation matrix is the eigenvector corresponding to smallest eigenvalue. Because in this case already I have explained the eigenvalues are arranged in the descending order of the magnitude. Now in this case I am defining a transformation. The transformation is y is equal to Ax minus mu x, that I am determining. And this transformation is called the KL transformation. This is the KL transformation. So this is my transformation matrix. X is the input vector, mean is the mean, already I have determined, and I am getting the transform data. The transform data is y. So this transformation is called the KL transformation. So now I want to see the properties of y. Y means the transform data. So first property is that mean of y is equal to 0. The first property is the mean of y is equal to 0. The output will be 0 mean. And also I can determine the covariance matrix of y. The covariance matrix of y is obtained from Cx and the transformation matrix A. So I can determine the covariance matrix. This I can determine the covariance matrix of y, that is nothing but the Cy. It is nothing but the expected value of y, y transpose. The mean of y is equal to 0. So that is why I can write like this. So E is equal to I can write A x minus mu x and A x minus mu x transpose. So, it is equal to A expected value of E x minus mu x minus mu x transpose and AT. So, from this you can see the covariance matrix of Y is equal to A Cx. So, this part is nothing but Cx and AT. So, I have determined this. So, here you can see the covariance matrix of Y is equal to A Cx A transpose. So, this is the covariance matrix, and you can see the covariance matrix of Y is a diagonal matrix. So, that means you can see the only the diagonal elements are available, and the off diagonal elements, all these elements are 0, all these elements are 0. So, Cy is a diagonal matrix. So, what is the meaning of this? So, already I have explained the meaning, that is, after the transformation, the transform data will be uncorrelated. The original data is highly correlated, but after the transformation, because I have the diagonal covariance matrix, after the transformation the transform data will be uncorrelated. So, that is the meaning of this, the transform data will be uncorrelated. And another thing is the eigenvalues of Cy are the same as that of Cx, and the eigenvectors of Cy are the same as that of Cx. That you can verify. Now, let us consider this case. So, that the reconstruction of the original data, but before going to the reconstruction of the original data, what I can show you, suppose I am considering one image, suppose. So, in this image, suppose these are the points, suppose 0, 1, 2, 3, 4, 5 like this, 0, 1, 2, 3, 4. Suppose in this image I have these pixels. So, 2D binary image I am considering, and in this case white means object is present and black means no object is present, that means 0. So, in this case I am considering white, this is the white portion. Corresponding to this I can determine the population vector. So, corresponding to which point the pixel is present. So, 2 and 2 suppose, because this point is 2 and 2. Suppose the another point is the 3 and 1, in this point it is present 3 and 1. The another one is the 3 and 2, the another point is 3 and 3. In this pixel the pixel is present, that is white pixel is present. Another one is 4 and 2. So, I can consider. So, this is my population vector. From the population vector I can determine the mean of this vector I can determine, and also I can determine the covariance matrix. After determining the covariance matrix and the mean, I can determine the eigenvalues and the eigenvectors of the covariance matrix, that I can determine the eigenvectors and also the eigenvalues I can determine, and after this I can determine the transformation matrix. The transformation matrix is A. The transformation matrix is obtained by eigenvectors. After this I can apply the transformation. The transformation is A x minus mu x I can apply. So, this is my transformation. So, in this example I am considering one image, and in this image I am considering the white pixels, these pixels, and corresponding to these pixels I am having the vector x. So, from this x I can determine mean, covariance and the transformation matrix, and after this I can apply the transformation. So, after the transformation, what actually I am getting? I will be getting a new coordinate system. So, my new coordinate system will be something like this. This is the direction of the eigenvectors u1 and the e2. So, application of this transformation, I am getting a new coordinate system whose origin is at the centroid of the object pixel. So, I can determine the centroid of the object pixel, it is the centroid of the object pixel, and axes of the new coordinate system will be parallel to the direction of the eigenvectors. So, here I have shown eigenvectors u1 and e2. So one axis is E1, another axis is E2. So I can say the KL transformation is nothing but the rotation transformation. This is the rotation transformation. That means it aligns the data along the direction of the eigenvectors. And because of these alignments, different elements of Y will be uncorrelated. So I am repeating this. That means I am doing the KL transformation. The KL transformation is nothing but the rotation transformation. It aligns the data along the direction of the eigenvectors, and because of this alignment, different elements of Y will be uncorrelated. So that is the meaning of the KL transformation. After this, I am considering the reconstruction of the original data. So in this case, you can see, so from this transformation, I can determine the reconstructed data, that is the X I can determine A transpose Y plus mu X, and in this case I am considering the orthogonal transformation A inverse is equal to A transpose. So I am having this one. So I can reconstruct the original data and the perfect reconstruction is possible. Now let us consider the transformation matrix is something like suppose AK. That is I can call as the truncated transformation matrix. In this transformation matrix, I am not considering all the eigenvectors. In the first case, I have considered all the eigenvectors for the construction of the transformation matrix. In the second case, I am considering AK. So in this case, I am only considering k number of eigenvectors of Cx. Cx is the covariance matrix of the input data. So I am considering k largest eigenvectors. So then in this case, I have how many rows will be there now? Because I am only considering k number of eigenvectors. So dimension of AK will be k cross n. So here I have shown k cross n. And in this case, just I am applying that KL transformation. So AK is nothing but the truncated transformation matrix. The truncated transformation matrix X minus mu X, and I am getting Y. So what will be the dimension of Y now? The dimension of Y is the k. So that means the dimension is reduced. The original dimension was n, and after the transformation I have the dimension k, and n is greater than k. So this is the principle of dimensionality reduction. So I can reduce the dimension of the data. So in the second case, if I want to reconstruct the original data, that is not possible because I am not considering all the eigenvectors. So that is why if I want to reconstruct from this one, I am getting the approximate reconstruction. So that is why it is x cap. So you can see I have this AK transpose, it is n cross k, and it is k, the dimension of the Y is k, and what will be the dimension of the reconstructed data, the reconstructed vector, the dimension will be n. So in the second case, the perfect reconstruction is not possible because I am not considering all the eigenvectors for the construction of the transformation matrix. Now in this case, I can determine the mean square error because the perfect reconstruction is not possible. So what will be the mean square error? So you can see here, the first term you can see, that is the lambda j I am determining, that is j is equal to 1 to n. That means I am considering all the eigen values minus I is equal to 1 to k lambda I. That means I am considering only k number of eigen values. So if I subtract these two, you can see here, so I am getting this one. So j is equal to k plus 1 up to n lambda j. So that is nothing but the sum of the neglected eigen values. So the mean square error depends on the sum of the neglected eigen values. Now implementation of the KL transformation in an image. So if I consider this is an image, so in this image I am considering n cross n image. In this n cross n image, you can see the columns are x0, x1, x2 like this. So in this case, every column I can consider as a vector. So this column I can consider as a vector, this column I can consider as a vector, and after considering this as a vector corresponding to a particular this column xi, I can determine the mean, and also I can determine the covariance corresponding to a particular column. The column is xi that I am considering, and after this I am determining the transformation matrix. The transformation matrix is A. So what is the E naught dash? E naught dash is the eigenvectors corresponding to the first largest eigenvalue. What is U1 dash? So U1 dash is the second eigenvectors corresponding to the second largest eigenvalue. So like this, I have to arrange all the eigenvalues that is in the descending order of the magnitude. So I am arranging all the eigenvalues in the descending order of the magnitude, and corresponding to the lambda naught, I have the eigenvector E naught. Corresponding to lambda 1, I have the eigenvector E1. Corresponding to lambda 2, I have the eigenvector E2, like this. And from this, I am constructing the transformation matrix. The transformation matrix is A. Also, I can consider the truncated transformation matrix, that is the truncated transformation matrix is AK. In this case, I am not considering all the eigenvectors. I am only considering the first k number of eigenvectors corresponding to the eigenvalues. So I am having the truncated transformation matrix. After this, what I am doing, I am showing the transformation here. So yi is equal to k cross 1, ak k cross n, and in this case n cross 1. So I am doing this one. So this is the transformation I am having. So after the transformation, my transform will be k cross 1, like this. So in this case, for the entire image, how to get this? So if I collect all the y's mainly, so I have the yi corresponding to, this is corresponding to xi. So for all the columns, if I can determine yi, in this case, for every xi of the image, we get yi. If the transformation of all the column vectors of the 2D image is done, then we will get the n transform vector, that is yi, we will be getting with a dimension k. And in this case, you can see it is the inverse transformation I am doing, that is the reconstructed value of xi, approximate reconstruction, because in this case I am only considering the truncated transformation matrix. So if I do the collection of all the xi's, then in this case I can get the reconstructed image. So collection of all the xi's will give the n cross n transform image. So in summary, I can say, so in the KL transformation, the eigenvalues are arranged in the descending order of the magnitude, and the transformation matrix is formed by considering the eigenvectors in the order of the eigenvalues. So already I have explained this concept, and also the reconstructed value I can determine by using this expression, and in this case I am considering the orthogonal transformation, A inverse is equal to A transpose. And in this case, suppose we want to retain only k transform coefficients, we will retain the transformation matrix formed by the k largest eigenvectors, and based on this I can define one transformation, that is the principal component analysis, that is nothing but the linear combination of largest principal eigenvectors. So this is the definition of the principal component analysis. So this is the summary of the KL transformation. So what is the summary of the KL transformation? The first, from the population vector I can determine the mean and the covariance, and from the covariance matrix I can determine the eigenvectors and the eigenvalues. The eigenvalues are arranged in the descending order of the magnitude, and after this I can determine the transformation matrix. Transformation matrix is obtained from the eigenvectors, and after this I can do the KL transformation, and again I can reconstruct the original data, and also I can determine the truncated transformation matrix. In the truncated transformation matrix, I can only consider the k number of largest eigenvectors, and based on this I can determine the truncated transformation matrix. Now you can see this, if I want to do the compression of compression of data, the compression depends on the value k. So how many eigenvectors I am considering for making the transformation matrix, and for reconstruction what information I need? I need the information of AK, and also I need the information of YI, that is the transform data, that information I need. From this I can determine X. X is the input data that I can determine. So this is about the KL transformation. The one problem of the KL transformation here, you see, the transformation depends on the statistics of the input data. So already I have mentioned, that is, in other transformation, the transformation kernel is fixed, but in this case you can see the transformation kernel is not fixed. It is derived from the input data. So suppose in the applications like the real time applications, suppose the non-stationary data, then in this case what will happen? For each and every instant I have to determine the mean of the data vector, and after this I have to determine the covariance matrix. From the covariance matrix I have to determine the eigenvectors and the eigenvalues, and after this I can determine the transformation matrix. Since the data is non-stationary, for each and every instant I have to do this. So that is why the real time implementation is very difficult. It cannot be applied. So that is why the KL transformation is not applied for image compression or the video compression, because for non-stationary data we have to compute all the parameters, mainly the mean, covariance, and also I have to determine the transformation matrix. So that is why the real time implementation is difficult. But if I consider the decorrelating property, so it can perfectly decorrelate the input data, because I am having the diagonal covariance matrix. So that is why the perfect decorrelation is possible by considering the KL transformation. Now I want to show the principal component analysis. What is the principal component analysis? Already I have explained. The principal component analysis means the linear combination of largest principal eigenvectors. So in the principal component analysis, again I am showing the same thing, the KL transformation. So I can reduce the dimensionality of the data set by finding a new set of variables smaller than the original set of variables, and retains most of the samples information, and useful for the compression and classification of data. So you can see I have the input vector x, and after this I am reducing the dimensionality. So the dimension is reduced because in this case the k is less than n. So PCA, the principal component analysis, allows us to compute a linear transformation that maps data from a high dimensional space to a lower dimensional subspace. And in this case, what is the high dimensional subspace? You can see. So this is the high dimensional subspace, and this is my low dimensional subspace. This V1, V2, Vn, you can see here, is a basis of the n dimensional space. And if I consider U1, U2, Uk is a basis of the k dimensional space. And suppose if I n is equal to k, that means in this case the dimension is not reduced. So here I have shown this example, one is the high dimensional space, another one is the lower dimensional space representation. And the information loss, that is, what is the information loss? Because of the dimensionality reduction, information will be lost. So the goal of the PCA is to reduce the dimensionality while preserving as much information as possible. This is mainly the minimizing the error between the projection in the new and the older dimensions. So that means in this case I have to minimize this. One is the original data, another one is the reconstructed data. That I have to minimize. Now how to determine the best lower dimensional subspace? The best low dimensional subspace can be determined by the best eigenvector of the covariance matrix of X. So already this concept I have explained, and these eigenvectors corresponding to the largest eigenvalue, and these are called the principal components. And here I have shown that principal components, that is nothing but the eigenvectors. So orthogonal direction of the greatest variance in data. So I have the first principal component PC1, the second principal component PC2, and in this case like this I have the principal components, that is nothing but the direction of the eigenvectors. These are the eigenvectors. So already I have explained, because of this the KL transformation, I will be getting a new coordinate system. In the new coordinate system, my new axis will be the eigenvectors. So here you can see these are my eigenvectors, U1, E2, these are the eigenvectors. So new axes are orthogonal and represent the directions with maximum variability. And the principal component analysis projects data along the direction where the data varies the most. and these directions are determined by the eigenvectors of the covariance matrix corresponding to the largest eigenvalue. So, this concept already I have explained. The magnitude of the eigenvalues corresponds to the variance of the data along the direction of the eigenvectors, and here I have shown that dimensionality reduction. So, can ignore the components of the lesser significance. So, you can see I am considering the principal component 1, PC2, PC3, PC4, all the PC like this I am considering, and you can see these principal components have the maximum information. So, I can neglect the remaining the principal components, because already I have explained the property, that property is called energy compaction property. So, most of the energy is available in only in few coefficients. So, in this case I am considering the largest eigen values and the corresponding eigenvectors. So, that means the PC1, PC2, PC3, PC4, PC5 I am considering, and remaining eigenvectors I am not considering, the principal components. That is, I can select the first p eigenvectors based on the eigenvalues, and I can neglect the remaining eigenvectors. So, what is the method? Again I am explaining this one. So, I have the vector, input vector. So, dimension is n cross 1. From n cross 1 I can determine the mean of this, and after this from the original data I can subtract the mean, and after this from this I can determine the covariance matrix. I can determine from the covariance matrix I can determine the eigenvalues, and from the eigenvalues I can determine the eigenvectors. So, this principle already, this concept I have already explained. So, from the input data how to determine the mean and how to determine the covariance, and from that covariance how to determine the eigenvalues and the eigenvectors. After this you can see if the C is symmetric, then these eigenvectors u1, u2, u3 like this from a basis, and in this case any vector x minus x bar, that is the mean, can be written as a linear combination of the eigenvectors, you can see here. And also if I consider the truncated transformation matrix, then in this case I can reduce the dimension in the step 6. So, this is the I am only considering the k number of eigenvectors. In the first case I considered the n number of eigenvectors. So, in the step 6 I am considering the dimension reduction step. So, you can see the dimension is reduced by this expression. And how to choose the principal component? So, already I have explained. So, principal components are selected based on the eigenvalues, the magnitude of the eigenvalues. And in this case the one condition you can consider. So, here you can see here the lambda I, this should be greater than, particular greater than. So, lambda I am considering, that is for the k number of eigenvectors from I is equal to 1 to k, and in the second case here you see the lambda I am considering from I is equal to n, that is for all the eigenvalues. Then in this case if this ratio is greater than a particular threshold, so based on this condition I can select the value of k. So, threshold I have to consider, for example I can consider 0.9 or maybe 0.95, and this ratio I can determine, and from this I can select the value of k number of eigenvectors. And in this case we have seen that the original vector x can be reconstructed using the principal components. So, this is my reconstructed information. So, this is my reconstructed vector. In this case I consider the mean, but in this case x approximate, because I am considering the truncated transformation matrix. So, that is why I am getting the approximate x that I can get. And also you can see the error also I can determine. The error means that low dimensional basis based on the principal component minimizes the reconstruction error. So, the reconstruction error I can determine, and the error can be determined like this. This is the expression for the error. Error is equal to 1 by 2 and summation lambda I, and in this case I am considering the neglected eigenvalues, the sum of the neglected eigenvalues that I am considering. Now, I have shown one example how to consider the PCA for face recognition. So, this example I have shown in my first class. So, this is the face recognition problem. So, we have the database and we have the input images. So, in this case I have to select whether this particular face is available in the database or not. So, this is the task of face recognition. So, my input images may be like this. It may be occluded or maybe some illumination variation I may consider, and in this case I have to find that particular face in the database. For this I can apply the PCA for the face recognition. So, this is my input image n by n image that I can consider as n square into 1 vector that I can consider, and in this case you can see the original face is this minus mean face I can determine, the average face I can determine, and that can be approximately represented by this. This can be approximately represented like this because I am only considering the k number of bases that is expressed in the low dimensionality space. So, you can see here, so each face minus the mean in the training set can be represented as a linear combination of k eigenvectors. So, here you can see this is the representation. So, each face minus the mean can be represented by a linear combination of the best eigenvectors. So, I have the eigenfaces like this. So, from the eigenvectors I can determine the eigenfaces. This is our eigenfaces. So, each face, this face is represented by represented as a linear combination of the k best eigenvectors. So, here in this case, that means if you see this slide here, these are my weights. So, this is my weight vectors and this is my weight vectors. So, representing faces onto this basis. And for the testing, what I have to do, for the test unknown image, the same procedure is repeated. So, first I have to do the normalization, and after this I have to do the projection on the eigenspace, and this is my weights corresponding to the test image. And for the face identification, what I have to consider, only I have to compare the weights that already I have explained for the training, and for the testing also this weight I have to compare, because already I have the eigen faces, and if this error is less than a particular threshold, then a particular face is recognized or identified. So, this is a face recognition by the principle of PCA. So, in this class I discussed the concept of the KL transformation, very important concept, the KL transformation, and after this I discussed the concept of the PCA, the principal component analysis, and after this I discussed one application. So, how to recognize face by using the PCA. So, let me stop here today. Thank you.